Hello everyone, my name is Evgeny and I'm a postdoc at Columbia University at Simon's Village Group. And today I want to introduce you another cool app in PDF in the cloud. So welcome back to PDF in the cloud. And you probably heard about structure mining, space group mining, and similarity mapping, but today I'm gonna introduce you the nmfMapping. What is nmfMapping? Is actually an application that allows you to disentangle structural phase components and their ratios from sets of PDFs or pattern diffraction patterns. And this will be relational data sets like a heating experiment, a time evolution, thermal evolution, or electric field evolution. Just a very brief introduction of what is non-negative matrix factorization. It's basically a mathematical tool that allows you to take a data set and to break it down to principal components to reduce the dimensionality of the problem to several principal components multiplied by their relative weight. So this will go with a cost function that will minimize the difference between V and the multiplication between H and W matrices. So you have your voltage versus time, and for each point in this graph, you measure your PDF. And probably you was wondering how you can break down all the structural contribution or all the structural elements that are evolving in the structure into something more clear and concise, and which will give you actually some physical meaning behind this. So this is exactly what nmf is trying to do. From this data set, what we'll have is a set of structural phases or structural components that are reconstructed into this H matrix. It's a set of vectors that will look very similar to an actual PDF, and you can actually try to feed them, and you will see that in many cases it corresponds to an actual structural phase. And another thing is it will give you out the relative change. So you can see very clearly that at some point during this cycling of your battery, you have an evolution of the structure or changes in the structural correlations of your materials. And for example, just at low voltages, you'll get the red phase, and at high voltages, you'll get more of the green phase, the blue phase, and in between, you'll get more of the green phase. All right, so let's now see how it's working. So you saw now very cool data set. Let's just spend 1 minute to generate all this data. So we'll click here, start. We'll go to the instructions first. Of course, you need to read how this is done. So we'll click it, and you can read the exact meaning of the parameters, what type of data you can use, and so on and so forth. And you can read more about this in this reference by Chao Liu. And so the first thing we do, we choose whether it's X-ray or PDF data. We choose PDF data. We upload the data, so it's going to be this exact data set. And we will open it. We'll choose a number of components, so we assume it's 4 components, can be something different, and we choose a range. The range will be 5, let's say 2 to, let's say 3 to be on the safe side, up to 30. And we can then explore what different ranges, how it affecting our reconstruction. And we choose an experimental data or a simulated data, and simply just submit. Yep. So the only so as you can see, it's very similar to what you saw earlier, a little bit different based on the range that you choose. So we chose 330, but we can choose something else. The overall trend is the same. You have this green phase that is emerging in between, the red phase that's emerging at the side, and another shade is emerging as we go to the low voltages. You can get more of the parameter like the reconstruction error or the component tables or the numerical values of all the components and their weights. And of course, you can download all this information and use it for your convenience. All right, that's all. I hope you enjoyed it. Go back to PDF in the cloud and keep enjoying. Bye-bye.